Welcome, everyone, and thank you for your time today. My name is Michelle Branzaleski. I'm the marketing manager here at Control Station. Today's webinar is something that hits home to every company, all of us personally, professionally, and it's improving sustainability. And today we're going to talk about how to do it with better controls. With me today, I have the director of Europe. He also handles the Middle East and Asia, Damian Monroe.
Hello.
Also with us today, I have Kerrigan Jones, who handles sales and support here at Control Station. Kara.
Hello.
All right. So we're going to go into a few things about Control Station first, and then we'll get into the main presentation. So a little bit about Control Station. We partner with our customers to solve process control needs using a combination of like world-class software. We have a few different types and expert services. Our offices are in the United States and Ireland, and we have successfully deployed our solutions to support facilities located in over 70 countries, and we're still growing that today. We are also proud to partner with 1 out of 2 manufacturers that are listed in the Fortune 500. Today's agenda, we're going to talk about sustainability, what sustainable manufacturing is, how you can achieve sustainable results. Then we're going to do a summary, and at the end, we'll do questions and answers. And on your toolbar, you will see a questions box. If you click on Open Pane, you can type in the questions, and we'll address those at the end. So with that, I would like to hand it over to Kara. Kara?
So the 3 P's of sustainability, what are they? The first one is people. This can include your employees, families, customers, suppliers, pretty much anyone influencing or being influenced by the organization or company. The next one is profit. Of course, we know the ultimate goal is to produce profit without waste. You can do this by reducing your carbon footprint, usage of natural resources and toxic materials, so on and so forth. The next one is planet. This concept can be implemented in many different ways. A couple examples of that would be active removal of waste, reforestation, and restoration of any natural harm done in the environment. Together, these 3 make up the pieces of a sustainable plan. And I'm going to toss it back to Michelle for a quick poll.
Thank you. All right, I'm going to launch a poll here quick. You should see it any minute. And just take your mouse and select all that apply. All right. So at your facility, your company, are you aware of a sustainable plan? Is there one there? Is it being implemented? Does your company seek out vendors that do have a sustainable plan, or you just have no idea if there's a plan at all? And I'll give everyone a few seconds to answer that. In the meantime, I'm going to do a short plug. Our next webinar is Halloween, October 31st, and this webinar is going to be on Process Control 101. And what we are going to discuss is your knowledge and test you on it during the webinar. All right. I'm just going to give this a few more seconds, and then I'll share the results with everyone. All right. I am going to close this and share it. You should see the results on your screen in a second or two. So 67% of people on this webinar, their company does have a plan. That's great to hear. 33% of the companies on the webinar seek out vendors that also have a sustainable plan, and the other 3% are not sure if there's a plan at all. All right, thank you. With that, I'm going to hand it back over to Carol. Thanks.
All right, so what is sustainable manufacturing? It is the creation of manufactured products through economically sound processes that minimize negative environmental impacts while conserving energy and other natural resources. This also enhances employee, community, and product safety. And with that, I'm going to hand it off to Damien for the rest of the slides.
Thanks, Cara. So how does sustainability apply to process controls? And we're going to start with an introduction into it and work our way into it. In fact, this next webinar will lead nicely on from this one, the one that's on Halloween, as it will give some detail to some of the aspects that we talked to here. I'm going to keep it relatively high level, but feel free with the questions to come through with anything that you want to further clarify or work through. So what is sustainability, and how do you get it? Well, there's one of the three tenets or levers of it: stabilize, optimize, and maximize. Each one of those has an effort to play or work to play on it, and it will give you the areas to focus on and to build up a structure to it. Sustainability is a definable, repeatable, transferable process that you're going to implement across your organization. It doesn't matter in what sector, whether it's in the accounts department or the recycling or the treatment plants or your supply chain. Everything needs to be definable, repeatable, and transferable, and it applies to our process control, to the PID layer as well, and I'm going to focus in on that. Really, we want to stabilize the process. We want to get those loops maintaining control, doing what they're told, doing getting the values so that their average absolute error is low, their oscillation is low, their reaction is correct and adequate for what you need to adapt to load changes, adapt to line speeds, etc. Once you've got that control and you stabilize your process, then the opportunity to optimize comes along and says, is the right place for this? Is this the right place for the process to operate? Or should we move our set points, move the way in which we control, or perhaps change the way in which we operate, how we start up, how we shut down, how we add an ingredient to the process? And from there, you can then maximize the efficiency and asset utilization, because you can then start to improve your use time. You can reduce your OEE, etc., to make most an effective use of the processes. This sustainable effort has kind of a loop to it, and it's an ever continuous process that you want to go through, from the decision of we want to become sustainable, to optimizing your process, getting those benefits, and then maintaining those benefits is what you want to do, reducing the waste, reducing the pollution. We have to, and we do accept, everybody accepts that we're in manufacturing. We are going to use energy to make products. Our customers are going to accept, or do accept, that energy consumption is necessary to make the products that they use and they benefit from. As manufacturers, our responsibility, as suppliers, or as you as manufacturers, have the responsibility to make sure that we are being as efficient with that energies and the raw materials as possible, and not seeing the waste. And then figuring out how to improve it, to, just because we've optimized, where do the improvements start to become apparent? Are we lagging in our startups? Are we doing a lot of wastage during startup? Where can we improve that process? And then learn from that information to bring into the next iteration. Maybe it's a production line expansion, it's a duplication of a production line, or at the corporate layer, it's a new plant that's been built to duplicate this plant, and taking those lessons learned and bring them over to the new plant, so the new plant starts up more efficiently and more effectively to run correctly. To measure this sustainability, you need to pick some key metrics. But I suppose also with this is the engagement of the various different business units within your organization. First of all, from a cost point of view, for an efforts expended, you're going to have to build a business case. Keeping that business case as simple and as focused as possible will be key to it. Process control is complex, but when you break it into its components, you can start to focus on the individual aspects to work through the weakness in those areas, and then build into this the relationships with the other systems around it. Those key business the metrics there: production rate, reliability, quality, number of outages, are all things that can be relatable across the organization, from the operations that have to run the plant, to the maintenance people that will maintain the plant, to the schedulers that will decide what product to run next, or what batch sequence to have. Including all of those organizations in your process optimization sustainability efforts is going to be key, because the benefits from that production area spreads out into all of those different units. We can translate those into technical or to key metrics that we can relate specifically to the PID, specifically to the process. Percentage time and normal. Is the process oscillating? Is there a high degree of variability or average absolute error where we're not spending time on set point? How is our valve health? How is our instrument noise or health as well? They're the mechanical devices. They're the physical devices in the field that are reporting and carrying out the actions that the control system wants to measure and affect. So it's key to measure that equipment, and is our optimization using best practices on those components to ensure longevity of life, but also that we're getting the best out of that equipment. Those metrics can then, you want to simplify them out into this justification, so that you can get your management team on board to engage in the process. What are we going to do here? What are we going to save? Where are we going to focus? What's the benefits of it? And these can come from many places. It's a lot of customers come to us and say, well, what's the ROI on loop tuning? What's the ROI on loop monitoring? And it comes in many different guises. There's obviously a financial, but there are some intangible results that can come out of it as well. Reduced man hours on the tuning process, reduced man hours on the monitoring process by having an automated system that's going to monitor for you. Those metrics, and they need to be recorded, and it's really key to start measuring those benefits from very early on. Obviously, at deciding what ones you're going to go after, but then look at the relationships between those metrics and feed that into a reporting, so that you're getting those values recorded from very early on. These kind of sustainability projects are a marathon. They're not a sprint. It's something that is going to take time to start and then to implement, and ultimately it's an ongoing process. It's a full mindset change, and that is going to give that information, or give give a place for all of this information that you have started to develop within your data systems. The simple ones that we like to look at are these: loops in manual, valve health, variability, systems at maximums or at constraints. They're values that can be related to very specific sections or departments. Loops in manual is an operational thing. Valve health is a maintenance and mechanical health system. Variability is your process. Your process control people have decided that this is the set point that this process should run at, and variability is going to give you those indications as how close or how far away you are from it. you know, that variability is something that is going to be the indicator of how good your sustainability and your optimization has maintained as the process gets older, as your systems start to age, as processes start to change. Loops that are oscillating and variability obviously tie quite strongly together to give you that information. So those 6 items there, 5 items should I say, are going to be key to that measurement to allow you to define where the improvements were made, you know, how and how you're going to get there. But measuring it along the way and keeping all the different groups in that part of that process and involved in that process is going to be key. So where do we start with this? And, you know, how do you get good control? Well, you know, to control something, you need to understand it. If you can understand it, you can control it. So that's fundamental to it. And I'm going to spend the next couple of slides talking about that fresh approach to having to understanding your system, because if you can understand the system, you can control it. It's the core to that. To understand it, you can control it, but to get there, you have to define that understanding. You have to say, you have to start to measure it, and you have to decide, well, what am I trying to achieve here? It's another one we like here is good control is simple. Safety, impact, management, profit, longevity, and equipment. Each one of those topics is key to understanding your process, understanding what you want to achieve. Anytime you change a process, you're going to have a safety implication potentially, in that you're going to change the way in which the process works. What kind of safety implications is there? What is the impact of changing your control philosophy, whether it's a tuning change, going to a more slower conservative or to a faster aggressive control? You know, what impact is it going to have on the management? But it's the management of your process. Is that it's going to, are you going to get better control? Are you going to manage your process better? Profit, quite clearly, if you get better control, you can make better product. If you make better product, you're going to have a better quality material to sell, to produce, and you know and you're going to use less energies to do it when you're more efficient with your energies, and less oscillation, less adding and subtracting of energies from that process. The last 2 there are 2 that are one of those long-term and very fundamentally sustainable. Longevity and equipment tied together in that you know, the longevity of a piece of equipment is how long will it last before it fails, and understanding your process will give you an understanding of the ability of that process to maintain this system. Does it scale up? Does the oscillation in the system cause stresses and strains on the process? The stroke, most valve manufacturers warranty valves for the number of strokes, you know, number of cycles that it can do, and they can be in the millions. But on a very aggressively tuned system with a system that has a high degree of oscillation, you're going to wear out those million strokes cycles quite quickly, and then that can exhibit itself in poor performance in valves, whether it's poorly seated valves or poorly acting valves. And longevity and equipment tied together with those 2, so that it gives you that the decision you make today needs to be sustainable long term, just rather than making a quick fix on a process now to aggressively tune it to get over that disturbance condition. And we'll talk a little bit about that in a few slides. But that approach to your tunings now is going to affect the longevity of the equipment, the safety of that equipment, and ultimately the ability to produce good quality product. So what is good control? And you can see a couple of charts there. The upper section is our set point and process variable. The lower is our output response to that. And there's fundamentally 2 types of control: aggressive control and moderate control. Which is better? Moderate is always better. Moderate is always better. Moderate is always better. I repeat that because I have yet to come across a user that has implemented moderate control on processes. Perhaps because the nature of industry and the nature in which the technology has improved to faster systems, more reactive systems, has lended itself to being more aggressive, more reactive in your control. But I have yet to see a system that has not benefited from reducing the aggressiveness into a more moderate function. Yes, there are times when aggressiveness is needed, but 95% of the processes I've come across have benefited from being more conservative, more slower, more moderate, and most importantly, respectful of the process, respectful of the process's ability to change. You can see the aggressive control. Yes, it's got fast disturbance rejection, and moderate has not got fast disturbance rejection, but disturbances are one of the biggest excuses or mistakes that people use when retuning a loop. They're trying to address a disturbance and using aggressive control to reject that disturbance. The PID will never remove a disturbance from your process. And I say that with using a strong word called never. You will never remove a disturbance with PID tuning. You may reduce some of it, but you will never remove it. The best way to fix a disturbance is to find out where the disturbance has come from and deal with it there. Potentially and probably, most likely, there's a PID upstream that is not managing its process and is causing this disturbance to come through it. And there are tools to look for those relationships, which again, we can discuss in future webinars. But that consideration, and I pause on this screen because all of you out there that are on this call, I would suggest that all or 95% of your loops are too aggressively controlled. It's something that is, and you will quite quickly see improvements if you start to soften out your control, and you get much more clarity on a process's normal oscillations when you clean out a lot of that fast aggressive control. Here's an example of a thought process that you need to go through when you're looking at a process and you want to understand how it controls so that you can define how you want to make changes to it. And we have a distillation column here through a condenser, and the liquid is collected in this reflux drum. The liquid is then fed down out of the reflux drum back to the distillation column. For those of you that are familiar with distillation processes, there needs to be a certain amount of return of those reflux liquids to keep the distillation column charged and operating. And the excess then is fed forward into the downstream process to where it will be processed and converted to whatever is required. Again, the distillation process is across all kinds of industries. It's in all sectors, but fundamentally the same. And you have to decide what is the primary objective on any of these processes. And we see here that it's maintain liquid level. So this reflux drum was put here to capture that liquid that's condensing off the distillation column. This purpose of this drum is to capture it, to keep a liquid seal on the distillation process, so we're not blasting vapors downstream on the process, but also to maintain this liquid level for constant and continuous reflux or return to the system. But also the excesses can then be flowed downstream on this flow controller for reprocessing or ongoing processing. It maintains column stability. We want this flow rate here for that stability and prevent environmental release, is what I mentioned. Now, again, with my comment on aggressive control, typically and level control is probably one of the most mistuned systems that we would come across. level control is a separate control philosophy. It's a separate process model that's used. But more importantly, the quality of the material in that tank is not affected by the level in that tank. And there can be a misconception that we want to maintain accurate level control at 50%. But that has no bearing on the quality of the liquid in that material. Now, if this was a temperature or pressure or flow, yes, absolutely. The set point that the temperature is at is going to affect the quality of the material that's in there. But level is one of those ones that we have to almost make a mindset change away from. We don't need to have accurate control, but what we do want is a consistency to that control and a more stable effect. If we think about why the designer put that tank into that system, that tank was put there to take these fluctuations, these variations in demand from the distillation process, and also the variations in the process downstream. So a degree of variability in the level should be accepted. Now, if we look at the performance of this process here, we can see as we move from left to right, we've gone from a high degree of oscillation and quite aggressive control to a lower rate of oscillation but a higher frequency, and then into a much more stable sequence there. Yes, we still have degrees of error on the process, but if we look at what the output is doing on that process, we can see the output was working really hard to try and maintain that accurate level control. As we dampened out the process, the system started to level out and become much more consistent. Some degrees of change to accommodate these variations, but we never hit the constraints. Most level control systems, most tanks are going to have a high level and low level, but so long as we stay inside those, we can then generate good control and be effective with the use of the reflux drum or the buffer tank or this system. The majority of tanks in systems are used as a buffer. There are a few instances where you do need accurate level control, but the majority of them are buffers that will just need to be used to allow the variation in that process. But with this, the real net effect of this conservatively tuned controller and the low oscillation in the output will maintain column stability. If we are being more consistent with our return back into that system, we will be more consistent in the distillation, the vapor generation in that process, and we will be more consistent into the liquid flow into that reflux drum, which is going to make the PID's job even easier. It'll just gain that stability. So much more conservative control is required. Again, an error that people will sometimes make is yes, but there is that time when I need this system to react quickly when demand downstream gets shut off or when we get a high flow rate in from the distillation column. The PID will not manage multiple models within a process. If we increase the distillation rate, we're going to have to increase the aggressiveness of the tuning. But you adapt your control, you adapt your tuning. It's called parameter scheduled adaptive control, or feed forward, or cascade. You will adapt your control to add this to it. So just because we got control doesn't mean that we need to stay in a very conservative mode. But if the majority of the time is steady state, you should use conservative control for it. So understanding the process is key to controlling it, because if we can understand it, we can control it. To understand that relationship, we need to exercise the process. We want to see that this wire out signal and the wire in signal, so that we're getting this relationship to understand between what the process is when we change the output, how does it affect my process variable? We're going to want to see that relationship there between those two, because this is key to the control and the ability of a PID or your control system to control that process. Is it needs to see the information coming back in from the process using our instrument and then make a decision on it to send it out to the valve, to the pump, to the positioner, etc. to give the actions on it. It's this wire out, wire in relationship that we're going to look at. How do we look at that? We want to exercise the process. We want to see how it operates. We want to understand how it operates. So we want this process to start reasonably stable. We want to be able to record these two values, because these two values are our wire out, wire in values. And we want to then exercise that process. So we want to move the output so we see the process variable respond. And during that time, we should keep the disturbances as quiet as possible. And another term I like to use is the first rule of PID Tuning Club is do not model disturbance-driven data. Is the key to it. A disturbance is something that the PID will struggle to control unless the disturbance is happening slower than the process model has indicated. You know, this disturbance-driven data is the mistake that most people tuning make, is that they try and tune out these disturbances rather than understanding the process and then understanding how you accommodate those disturbances into that. A controller of PID is going to use a first order plus dead time model to understand this relationship. A first order plus dead time, again, somewhat of a topic for a later webinar, but we'll use this as the process by which we understand our process. First order plus dead time model is the relationship of that wire in, wire out. So it's how much output makes how much process variable change. So how many % of output change gives us 1 degree of temperature change is the language, or it's what's called the process gain. How much process do we gain when we change our output? The process time constant is the how long does it take to change? And again, at the number of times I've talked to PID tuners, and they go, well, I don't know my process time constant. Process time constant is fundamental to understanding how quickly or slowly you can control your process. The process time constant is the amount of time it takes to change, the amount of time your process takes to change. If your process time constant is 25 minutes, for example, you will not be able to change that process in 1 minute. You will not be able to respond to a change in 1 minute. It's mechanically, thermodynamically, technically impossible. So process gain, process time constant. The final one is the dead time, is the amount of delay it takes to change, the time of change. It is the time it takes from when you wire out and open the valve to when you see the change start to occur. It's the amount of time it takes from the valve opening to the heat being increased in your heat exchanger, to the steam coming in contact with the plate exchanger, transferring to the liquid in the other side of the plate exchanger, that liquid flowing out of the discharge of the plate exchanger and hitting the instrument downstream. It's the dead time in the process from when we ask to when we start to see. And it's a number that can give you an indication of your ability, how quickly you can control. The bigger the dead time, the slower the time to control will be, and effectively the more variance or float there will be in a system. Now the dead time is only a concern when its ratio to the time constant is close, or they're comparable. The way I describe that, a 10-second dead time on a process that takes 10 minutes to change is not insignificant, but a 10-second dead time on a process that takes 20 seconds to change is a problem, is something that's going to cause you a degree of trouble or difficulty to get good control on it, because you're spending half of your time waiting for something to happen, and then you've only got, you know, twice the amount of time for the time to be able to change. Large dead time to time constant ratios will develop into an oscillating, or a system that has a degree of float in it. Trying to be more aggressive with your controller, with your tuning parameters, your integral time will not help you. It's because the integral time can only work with the process time constant as a relationship. And we will talk about that in a couple of minutes. This first order model then is key to understanding that process, because from that we can then get this relationship from the wire in, wire out. You know, the how far, how fast, how much delay, you know, is this process gain values here. But this relationship and understanding how your pipes, pumps, tanks, instruments, and valves all interact with each other to feed this signal back into the control system is fundamental to controlling it, because if you understand it, you can control it. A good example, this here is a good example of that process by which to look at it. And again, we have a number of these case studies. If you're looking for specific case studies on processes, by all means, please reach out to us. We can share some of these with you. In this example here, thinking about that wire in, wire out relationship, and this is a before and after plot on this system, just so you can see that this was a steam loop, and it had a degree about 40% overshoot on that process. Again, because the approach or the control to it was trying to react as quickly as possible, trying to react as fast as possible to try and make the change make the process do what we wanted it to do. And we can see here this on the chart here, this green is the set point changes. This sine wave here, sine wave shape here is the process variable. I know the colors are not great on the plot there. And then this was the output here. But I want to draw your attention to particularly the first section of the output here compared to the section of the output here. And we can see here that the process set point changed and the output reacted to it. It used the PID parameters to do it, and it stepped with the proportional value, and then it tried to integrate over time. But the integration value was not respectful of the process time constant. The process time constant is the amount of time a process takes to change. Post the tuning and the retuning of it, we can see here we had a large proportional reaction, and then we integrated much more conservatively over time, and so that we worked the process up to it respectfully of the process time constant. The one of many takeaways that I want you to take away from this discussion here is your integral time must be very respectful of your process time. And the way to do that is to make them the same, so that your integral term is equivalent to your process time constant. You can then change your aggressiveness on your proportional, and you can get those values to match in there to it. A couple of other takeaways on this. You can see the proportional and integral integrated over time, but we never overshot the process. We approached and attracted. It's something actually that is become very prevalent in industry in the last perhaps 5 to 10 years, I suppose, is that the overshoot is no longer acceptable. If any of you know the Ziegler-Nichols method of tuning, etc., there tends to be this quarter decay approach, you know, push the loop so that it starts to oscillate and then back it away a little bit. The unfortunate thing with the way in which that, in its purest sense, it will get you there, but you have to make the system go unstable before you will get control of it or understand it. But that's not always possible, and it's not always followed to the proper amount of oscillation, because you just can't do it. it leaves the system in a very unstable state, and the stability of the process, it's maintaining control, but all it needs for the process model to move one way or the other for the process to go unstable. And this is in reality what has happened here, is that the process is generally unstable. Here now it's much more respectful of the time, and it's reacting to it to settle out on the process. You know, back to our stability, you know, a small gain on a single loop can build up to being quite a large benefit over a longer term, over a long time, and they're very achievable. I know all of your processes out there have these kind of potential opportunities, and if you want to discuss some of those, we can certainly show you some results and how to measure those and how to get them. Really, if you think about the amount of energies that your process is using right now, and think of a number of between 3 and 5% of that, this is the amount of potentials that are saving out there. PIDs are the biggest energy consumer on your process, or at least they are the manipulators of that energy. They are the ones controlling the steam valves and the pumps and the chemical dosings and all of those systems. So optimizing those processes will give you sustainable returns almost from day one when you start to make improvements like this on a process. Yes, the PID is going to use energy, but it needs to use it as efficiently and as sustainable as possible. Next slide is just the summary of it. So what does that mean for us with our sustainable approach to it? Sustainable is definable, transferable, and repeatable. I didn't really talk about the transferable and repeatable is that if you set the process up and you understand your process correctly, if you set up your optimization process up, you can be transferable and repeatable on that. It doesn't matter whether it's your engineer of 20 years experience in the petrochemical industry or your recent college graduate, so long as you follow those rules and that recipe, will get you the same result on it. Understand the process, measure it, get the values of it, and then make decisions on it. Yes, I haven't talked about the mathematics of converting a first order plus dead time model into tuning parameters, but a lot of that is readily available through our software, but it is also through mathematical calculations that you can do based on the model fits that you have and the vendors that you're using. There is going to be an investment in time. There's going to be investment in capital. Is something that it's not significant when it comes to the overall investment that you've made in your process, but the savings can be hugely significant because that plant is going to be running for the next 15-20 years. So ensuring that it's sustainable in the long term is going to give you those returns, those $1,500 or euros per piece of equipment per year. But again, I'd ask you to go and count the number of PIDs that are on your process, and the amount of energy that they are in control of is going to be significant. Sustainable is shareable, transferable. You know, the benefits, the savings, all of that is something that is going to come through with management, and using those little gains on individual components. You know, have you got 10 air handlers? If you made each one of those 1% more efficient, that's going to have a real value on it. Continuous improvement, fine tuning and continuous improvement. Another mistake we see regularly is that people will tune a loop and say, okay, done, that's it, well, let's walk away, we don't have to look at that one again. But once you clarify the data and the information so that the process is now stable, you are going to expose the other opportunities. Your process people are probably going to look at, well, now that we've got control, we can move closer to a constraint. I would actually rather this system runs 5 degrees more warmer or hotter, but we could never risk running up against that trip point or that exothermic reaction, etc., etc. There can be many reasons for it, you know, but it can also expose maintenance opportunities in that you have reduced the wear and tear on a process, that you've reduced the equipment that is working less hard and is going to allow you to extend your maintenance practices. You're obviously not going to do that in day one, but it's a long-term process, a long-term thing. Next slide is questions. So Michelle, back to you, just to see has anybody come in with any questions?
Okay, Damien, thanks for sharing your experience and setting everyone off in the right direction with sustainability. If you have a question for Damien, please open your questions bar. There's a little logo on the right-hand side. Click open pane, type in your questions, and we will get to them. If you want to go to the next slide where people are typing in the questions. Can you go to the next slide, please, Damien?
Oh, sorry, apologies.
It's okay. We're live, people.
I was listening for questions.
All right, if you have your cell phone handy with you, whip it out. Take a snapshot of the QR code. You will have access to industry-specific papers, blogs, white papers. You can sign up for the next webinar, October 31st. So if you want to do that, we'll leave that up for a minute. Damien, I have a question here. Based on your experience, what specific technical KPI do you suggest someone in the chemicals industry?
You know, the quick fix and the one that we see the gains from initially, particularly if you're looking for justification, is percentage time and normal. Your control system was designed to run in automatic. Your company has spent millions, if not tens of millions, on putting an automated control system in there. For it to run in manual is a mistake, a flaw, a weakness. So tracking your percentage time and normals is a really quick way of, does two things: understands how good or bad your control is, but also shows you the opportunity where we can make improvements. It's again something I would see with companies is go, well, how long has that loop been run in manual? That always runs in manual, or we can't control that loop. And what happens that you can't control it? The percentage time and normal will give you opportunities or places that you can chase, that you can understand where the process is struggling. Operations go, oh yeah, we always go to manual at 9 o'clock in the morning, just before that side stream comes into the process, because we know it doesn't manage to change. But they forget to put it back into manual an hour later. You know, that's sequential, that's procedural, that's automate that process is you know, and you can improve those percentage time and normals very quickly. Some of it is habitual. Some of it is operations go, I just turn it to manual and set it to 42% and it sits there. It runs a little hot or runs a little cold, but it gets me over the process. So KPI number one is percentage time and normal is one. Oscillation would be my second choice. Look at your processes and look for oscillation. Then understand where those oscillations, how they've gotten into your system, where they've come from. We have tools to help on those, but as I said, you can quite quickly look at your historian trends and see which loops are oscillating, and then that's where you should focus. If a loop is oscillating, reduce the proportional, slow down the integral, and you'll get improved results.
Thanks. Okay, if you can go to the next slide. We just have one more final fun thing to do. I will pull it up here in a second. Oops, wrong one. Here we go. All right, you should see it on your screen in a second or two. Click all that apply. Just take your mouse and click on them. Please have someone like Damien from, control station provide more information about virtual training classes, a possible software demonstration that we could for oscillation, turnkey control loop performance monitoring, or PID loop tuning solutions. Okay, I'm going to leave that up for a little bit here. Give everyone an opportunity to respond. All right. With that, Damien, would you like to share anything else?
Just on that, you know, we don't bite. I'm sure. Well, you may have questions coming into this webinar, or it's perhaps raised questions. Please feel free to reach out to us. It's something that we have a wealth of expertise in process control and PID. I would, if you've got colleagues that are struggling with understanding PID, perhaps our college graduates that have come out of the mathematical world of college PID education, we have a much more practical approach to PID control, and it's understanding that process and then using the available tools, the PID block, to get effective control. Look up our PPC class. It's a very useful class.
Thanks, Damien. All right, one more slide. If you would like to contact Damien directly or Kathy Sweet, they're both in the EU, Ireland. There's Damien's information, Kathy Sweet, his colleague. We have Brian and Alessia in North America and their contact information. So we're getting pretty close on time here. Damien, Kara, if you want to come back in. There we go. All right. So Damien, Kara, thank you so much for doing this today. Appreciate it. There's a lot of good information in there. Like I said at the beginning, sustainability affects all of us personally and professionally. So like I said, if you have any more questions, please don't hesitate to contact us. And hopefully I'll see you all on October 31st, Halloween, for Process Control 101. Thank you, everyone.
Which will bring on information from what we just talked about. So we will be continuing the story in the future webinars.
All right. Thank you.